You are watching the 9.6 lesson video on correlation and causation. When we talk about correlation and causation, we are always talking about two variable statistics or bivariate data, what we actually have been talking about for the past couple of lessons. So when we were talking about the two-way frequency tables, we were also talking about scatter plots and regressions. Obviously, we were graphing an x and y axis, and both of those had to be two different variables. So in exercise 1, we see that Roberto has a bag of 150 Skittles, and each day he eats some of the Skittles. The situation is modeled below. And what we see here is not only have they given us the table of what's going on with the Skittles, they're showing us two different graphs. And as you can see, the blue points, or on your paper, they probably don't look blue, on mine it does, but the blue points all look the same. But one of them has a linear model and the other one has an exponential model. Now, some of you might say, well, why in the world would they even use a linear model? It doesn't look like a line. Why did they do that? Well, this is going to help us to understand correlation. So the term correlation. All right, so A says find a line of best fit of this data and round your values to the nearest tenth. Well, the nice part about what they gave us is they've already given us the line of best fit. It shows it right here for actually both the linear regressions, the line of best fit, and they did the exponential regression. So our job is just to round to the nearest tenth for both of our equations. So here we have y is equal to 153.1 plus 37.6x. Oh, so this is not written in mx plus b format, but you can see here's our m and here's our b. The same thing, it's addition, so it's commutative. We can write it in whatever order is given. But the one thing that they haven't given us is the value of r, and I don't even know what that means just yet. Let's hold off on part b. And I'm going to hop over to D because it says find an exponential regression, which it looks like they already did that for us. And it says to round the values to the nearest tenth. So y is going to equal 218.5. And that's going to be multiplied by, so the nearest tenth is about 0.4 to the x power. Okay, now that we have our equation shortened, let's read on, because both B and E are telling us to find this value of R rounded in this place to the nearest hundredth. So, all right, you know what? Let's go through and actually do this regression. I have all the data typed in my calculator. I'm going to run a linear regression first, and I'm just going to do mx plus b, even though we have it written in the other format, but that's fine. So what are we dealing with? Days is our x, and Skittles is our y. Just hit OK. I see r squared. I just want r. Did they give that to us? Oh yeah, there it is. It's right below the r squared. So if you look on the calculator, we see r is going to equal, nearest hundredth, so this would be negative 0.9. Is it going to be 1 or 2? Well, it's followed by a 0, so it's definitely a 1. All right, so that was a linear regression. I'm going to skip over to F in the equals box again, right here, and I'm going to run now an exponential regression. Same deal, I'm still dealing with days for my x and Skittles as my y. And here's my data for the exponential regression. Still don't see an r, but hey, there it is. So in this case, the r is equal to negative 0. Oh my goodness, 99. That's really close to -1, isn't it? A lot closer than the other one is, but still -0.91 isn't that far off. So what does this tell you about your linear model? And what does this tell you about your exponential model? Well, we don't know yet. I don't even know what R means. So let's read down here. Okay, what is R and what does it mean? Oh, this is great. Okay, so the value of R represents the correlation coefficient. Okay, big deal. I still have no idea what this means. But what does it tell us? So it tells us if our function is a good fit, or obviously it could tell us or it could tell us if it's a bad fit too. It ranges from -1 to 1, where -1 is perfectly negative data and +1 is perfectly positive data. Okay, now I'm starting to see. So look at our negative. This is a -0.91. That's pretty close to -1. But look at here, -0.99. That's really, really, really close to -1. This is almost perfectly negative data. If you look at the exponential regression, which you would probably agree that this exponential line or curve models the data much better than our line of best fit does. Okay, and we can categorize our data as strong, moderate, weak, or no correlation, and it can also be positive or negative. So if it's increasing, it would be positive. If it was decreasing, the correlation would be negative. So let's just get a little bit of practice before we draw our conclusions in C and F of what R would be in these examples down below. So I don't know, what do you guys think? This data is looking pretty strong in the first one, so R, it's increasing, so maybe we want to say that something like, I don't know, 0.97? That seems about right. Next one, a weak positive correlation. Maybe that's something closer to, let's say, I don't know, 0.3. I guess no correlation would be halfway between -1 and 1, which would be 0. That kind of makes sense. I jumped all the way to the end here, but that kind of helped me to justify why I picked 0.3. Strong negative correlation, we could say same thing. So I'd probably give that maybe a -0.97-ish, just like what we did here. A weak negative correlation, that one's a little bit stronger than the weak positive, so maybe we're going to say that is around like a -0.5. And then a moderate negative correlation, well, it's negative, so negative point, I don't know, like 7-ish, 6.5, 7-ish. Let's say -0.72. All right, now if we go back up here, where it asks us a question, what does this tell you? What does this correlation coefficient tell you about our linear model? That it is a good fit, but could be better. And what does this -0.99 tell us about our exponential model? This is a great fit. And also, let's talk about the fact that they're both negative, which means it's a good fit. We would say it's a pretty strong to moderate negative correlation. I'm just going to abbreviate. And then for part F, what does this fit tell you? It's a great fit. This is a very strong, it's actually almost perfect, negative correlation. Okay, now we've talked about correlation, we should also talk about causation. And part of the word is actually cause, so something causing something else to happen is what we call causation. And we can actually have two variables that could be strongly correlated just by happenstance, or maybe it's just something that typically happens, but it might not have a causal relationship. If we look at all the examples in exercise number 2, what we're going to do is determine if a causal relationship actually does exist, and then if so, what variable causes the other to happen. All right, A. The high temperatures in New York City and the number of water bottles sold. So I would think, I guess you could probably go either way on this one, but I think that this is a causal relationship. I think that the temperatures are going to cause the increase in number of water bottles. Okay, B, a person's height and a person's shoe size. I would say that this is a no. This is not causal, because it's not like if your feet grow that you automatically get taller, or if you get taller, your feet automatically grow. It just doesn't always necessarily happen that way. Okay, C, a person's weight loss and the number of hours a person spends in the gym per week. Um, I got, I think with this question, they wanted you to, the person that wrote this wanted you to say that it is causal, because if you typically spend more time working out, you're going to lose weight. So I guess we're going to go with that. But yes, I do agree with you that sometimes that might not happen. So we will say that this is a causal relationship. We're going to say that the hours at the gym would cause weight loss. Okay, and D, so the years of education a person achieves and the salary that person starts at upon entering the workforce. Sadly, this is not a causal relationship. And let that be a lesson to all of you. Don't spend too much time at college, because even if you spend 7 years there, it doesn't necessarily mean that you are going to make an awesome salary coming out. Okay, exercise 3. We have a scatter plot, and it's comparing the number of bags of popcorn and the number of sodas sold at each performance of the circus over 1 week. So it's asking us what conclusion could be drawn from the scatter plot. There is a negative correlation between popcorn sales and soda sales. Well, this is not negative. The data is increasing, so definitely this is going to be a no. Okay. 2, there is a positive correlation between popcorn sales and soda sales. I think that that might be a good answer. We're going to hold off on crossing that off for now and read on to make sure that we pick the best conclusion, because a lot of times there could be 2 answers that seem correct, but one of them is better than the other. 3 says there is no correlation between popcorn sales and soda sales. That's not true. If there wasn't correlation, it would have looked like a snowstorm of points. So we can go ahead and get rid of that. Number 4, buying popcorn causes people to buy soda. I don't know if we can necessarily conclude that, because what if it was the other way around? What if you bought soda and that caused you to buy popcorn? We can't conclude that just from this scatter plot, but what we can conclude is that there is a correlation between the 2 values, but maybe one does not cause the other to happen, or we can't really conclude that. We don't know. All right, number 4, what type of relationship exists between the number of pages printed on a printer and the amount of ink used by that printer? So what will happen? The more ink that we use, so the more ink that's used, what will happen? So we use more ink, and we're going to, actually, hang on, let's read this. Let me read this one more time. I'm backing it up. Okay, you know what? Scratch this idea. I'm going to graph this. So I'm going to create a little chart here. And we are dealing with the number of pages printed and the amount of ink used. So the more pages we print, the more ink that's used. That's kind of what they're going with here. So the number of pages, as that gets bigger, the ink, we're going to have some type of relationship that looks like this. So if we look, we know that this is definitely positive. So answer choices 3 and 4 are out. And is one causing the other to happen? So if you print more pages, are you going to use more ink? And the answer is yes. So this is actually going to be both positive correlation and a causal relationship.